Hello there, everybody. My name is Heinrich Dinkel, and I'm here to present our work for the DCASE 2021 workshop, which is called a lightweight approach for semi-supervised sound event detection with unsupervised data augmentation. The work was mainly done at Xiaomi. First, I go here over our outline. I state the problem that we try to solve or try to challenge here. Then I go quickly over our approach, which we try to the above stated problem try to solve using learnable clip smoothing, using unsupervised data augmentation, and our model. Then we go over the results using our model, and lastly we do a quick discussion or a conclusion. First of all, we try to a main problem in sound event detection is that we have two outputs usually. One is trainable during training, which is the clip level head, means that we have for one clip of 10 seconds, we have one or multiple labels available. And usually we have also an untrained frame level head, in standard classic sound event detection. This is untrained because we don't have full supervision on that head. But actually what we try to have during evaluation is that we train it on clip level, but we obtain predictions on frame level. Problem is that due to, let's say, some reasons, for example, usually the outputs of the frame level head are during training summarized to the clip level in order to be backpropagated using mainly a nonlinear combination of these frame level weights. That means that it's not entirely sure what is the output of the model given for example a frame level output. What is the clip level output? I mean, would he output that more than the other? Some a little bit more than the other. So here we see an example of this behavior. We have here two labels being speech and vacuum cleaner, which are here denoted in blue and yellow, which are the frame level outputs, which are the only two clip level outputs that are predicted by our model here. But there's also a third, or also there are other labels. For example, Blender is also predicted sometimes with a probability higher than 50%. But the clip level head is actually not predicting this label. So that means, well, it's arguably, is that label really present or is it not? So what we try to, when we try to avoid this kind of problem, we use learnable clip smoothing, which is actually just a very simple algorithm where, as said before, we have two kinds of outputs here, a clip level output and a frame level output. And usually during training, we aggregate the frame level output to obtain the clip level output, and then our learnable clip smoothing just multiplies that clip level output by each frame level output. That means just we just multiply back all of the values which are predicted for the clip, so we actually just squash any probability which is not predicted by the clip level head. We call that learnable clip smoothing because, well, in that data set, actually, there is a loss for the frame level, but it's actually synthetic, but still we can use that loss. So this thing will be actually learned. You can also do that thing without any learning, still works. But that one is, of course, a bit better when we have a bit better supervision. Second of all, we use unsupervised data augmentation, UDA. UDA is actually just a combination, another method which is compared to the much more popular mean teacher method in sound event detection, where we can use unlabeled data in order to enhance our models, well, just accuracy or in this case event or PSDS scores. So UDA usually uses first on the left side supervised training regime. This is standard. We have an X, Y, and then make a binary cross entropy, which is standard in the challenge, loss between the predictions and the ground truth. And then we also do a consistency learning framework where using UDA, where we have another X which is actually unlabeled, can be also labeled but actually unlabeled, and then do augmentations on X. And then go over our original model, both of these samples go over these two samples, and then we compute a consistency. It just means different kinds of augmentations shouldn't make a difference, so it should be consistent between two samples which are originally the same but just have been augmented. And for our model is, well, you can see that in the here in the link. It's a very simple like CRNN framework, usually not very big. Is like a previous work of mine. Then to the results, here we can see like on the left side the baseline, and on the right side like the proposed clip smoothing. Baseline, like when we actually directly check like from the baseline, we have 3 types of data: weeks, synthetic, and unlabeled. So we always like add them up like in a row. And as we can see like from the results, actually clip smoothing overall completely improves performance. Also UDA improves performance, like for both like our baseline and like using the proposed clip smoothing framework. So we get like a nice performance boost for PSDS 1 and 2, and also like for the event and like for all metrics actually. And like in the challenge results, like in the DCASE 2021 Task 4 challenge, we got overall with our approach here like 7th place. But what we then forgot actually, or like, well, didn't want to do medium post-processing, where most other like the top 6 all use medium post-processing. So we later asked like to have our results reevaluated using medium post-processing. And after reevaluating, we got these results where, well, our work would be around 5th place when we would just simply do exactly the same stuff, but like with medium post-processing. We are by far the smallest competitor in the entire challenge. Like, well, as you can see, like our smallest model is like has 2 million parameters. And it's also like overall the 2nd best model when we would consider that we have only a single model. So like for both PSDS 1 and 2, we submitted a single model, where like the 1st, the 3rd, the 4th place, they submitted 2 separate models which are optimized for each of the both scores. And then, well, that's it. Thank you very much for listening. And the code is also available in the PPT. So yeah, have a look.